Hello everybody, this is Statistical Computing and Machine Learning. Nicholas Zabaras is speaking. So the lecture today is about the Metropolis-Hastings algorithm, one of the most fundamental algorithms for sampling. So let's see some of the topics that we will cover today. So I will start with a brief review of Markov Chain Monte Carlo. I will give you an example of the autoregressive model and calculate what's called the Autocovariance Function. And then I will provide different versions of the Metropolis-Hastings algorithm, the original algorithm, the independent Metropolis-Hastings algorithm, and the standard Metropolis-Hastings algorithm. I will clearly define what the transition kernel is, what the proposal distributions can be, and discuss about the conditions of reversibility, irreducibility, aperiodicity, and then of course give you a number of examples. We will proceed with discussion of using a mixture of proposal distributions, using a composition of Metropolis-Hastings kernels, and then I will give you some ideas on using hybrid algorithms. Maybe you can think an algorithm where you sample in one step some components of your high-dimensional vector using Gibbs sampling, and maybe the other components using a Metropolis-Hastings algorithm. And then I will give you some possibilities for extension of the Metropolis-Hastings algorithm. I will finish the lecture today with a very brief discussion on the Hamiltonian Metropolis proposal, which is a very powerful method with a motivation coming from molecular dynamics or atomistic modeling. Some of the references for the lecture today, the key reference that we're going to follow very closely is the lecture notes from Arnaud Doucet on statistical computing and Monte Carlo methods. You can find these resources online with lots of details and further references. And the remaining of the references and some of the examples in the notes, I will be using other references and I will be providing them as we go along. All right, so the goals for the lecture today will be to review the fundamentals of Monte Carlo, Markov Chain Monte Carlo, review the various forms of the Metropolis-Hastings algorithm, and then discuss about mixture and composition of proposals and kernels, understand how to implement hybrid algorithms, and then some very brief review and understanding of what the Hamiltonian Metropolis proposal is all about. All right, so let me start with the fundamentals of Markov chain, the way we have seen them in earlier lectures. So if you remember, a Markov chain is sort of an algorithm that generates a sequence of random variables that I call them here xn, and 0 to infinity. And what we need to generate the sequence is we need some initial distribution, and then we need some transition kernel, or some probability that will allow us to basically, through this rule, to go from a state xn, let's say at time n, to a state xn plus 1 at time n plus 1. And we will see that, for example, the Metropolis-Hastings algorithm implicitly defines for us what this transition kernel is. Now, in practice, we don't have a transition kernel. What we have is a target distribution, and the objective is, can you define some rule of transition from xn to xn plus 1 so that this Markov chain converges to a target distribution? So it's the other way around, right? So you don't start with k and say what distribution do you converge, but it is the other way around. You have a target distribution in mind and you want to go around and say, find me a kernel that somehow, if I do this iterative process asymptotically, I will be having pi of x as my stationary distribution. Okay, so let me give you a very particular example, and that's the example of an autoregressive model. So you can see here the key equation for an autoregressive model. Simply xn is rho xn minus 1 plus zn. Zn comes from a standard Gaussian, so that's a noise variable. And to be sure that this xn doesn't blow up, I take that the absolute value of rho is less than 1. Now, the initial distribution for the example that I'm going to take will be a standard Gaussian, but you can imagine that literally to where this chain is going to converge doesn't really depend on the initial state, or at least we don't want it to depend on the initial state. But right now I am taking the initial state to be sampled from a standard Gaussian. Now you can show that the expectation of xn is equal to 0, and you can show asymptotically that the variance converges to 1 minus rho squared. And you can see from the analytical form of the variance of xn, you have these terms rho to the power 2n, and that's why you need the absolute value of rho less than 1, so that those terms go to 0. Okay, and the transition kernel, if you want to write it as a distribution, it is this simple distribution. So given xn minus 1, the xn follows a Gaussian with a mean rho xn minus 1 and a variance 1, where again the absolute value of rho is less than 1. And you can show that asymptotically xn basically are samples coming from a Gaussian with a mean 0, and as a variance, this asymptotic variance 1 over 1 minus rho squared. So this is where the Markov chain converges. And again, I remind you, even though right now we start with the autoregressive model and we say it converges to this distribution, in reality, and we will see this in the lecture today, we have to go the other way around. We're going to have a target distribution and try to find out a rule or maybe an algorithm that somehow gives us a Markov chain that asymptotically converges to the target distribution. So let me take the particular case of rho equal to 0.5, x0 coming from the standard Gaussian. I can compute the sample variance using samples from the Markov chain, where the mean is approximated with a sample mean, and you can see that the estimated variance converges to the asymptotic variance that I gave you before, which is the asymptotic variance is 4/3. So that's 1 divided by 1 minus rho squared, where rho in this case is 1/2. And if you take samples from this Markov chain and create a histogram, you can see that actually you do get the actual target distribution, which is a Gaussian with mean 0 and variance 4/3. Okay. So in this particular example, I started with an initial state of being a sample from the standard Gaussian, but you can start with some arbitrary value, and you can see again the generated samples are actually also give you the same target distribution, this Gaussian that we had before. And of course, I am not plotting the same diagram for the variance that I had before, because certainly the variance, at least in the early steps of the algorithm, will actually give you irrelevant values, because x0 minus the expectation, or an estimate of the expectation of x, will be a very big number. It would not be sensible to do that plot, but certainly, as we have seen earlier in earlier lectures, if you consider a burn-in period and you start taking averages after that burn-in period, you can plot the variance and the results will look very good, and it will converge to the correct asymptotic variance, exactly as we saw in the schematic in the earlier slide. Okay, so again, we need to construct a rule or a transition kernel that tells us how to go from xn to xn plus 1, and we need to do this in a way that somehow it will give us a Markov chain that converges to a target distribution. It will give us a Markov chain that if we calculate averages along that chain, those will correspond to the correct estimation of the expectations under the target distribution. But we have a problem, and that problem is the samples that xn that you get from Markov chain, they are not independent samples. I mean, if you think about the autoregressive model, right, xn plus 1 is rho times xn, so xn plus 1 and xn are highly dependent, so we would not, with certainty at this point, being able to say anything about convergence or rate of convergence, simply because xn are not IID samples. So now it will come up that somehow this approximation using a Markov chain, it will actually converge to the true expectation of f of x under the distribution pi of x asymptotically. We don't really know how fast the convergence is going to be or how many samples we need, and certainly we will not be able to say that the variance of this estimator is our standard Monte Carlo variance, which is the variance of f under pi divided by n. So the question is, can we come up with, for a Markov chain, can we come up for some estimation of the variance of this estimator I hat? So we're going to do a few assumptions to just get an idea of what the variance of that estimator is all about. So this is our estimator, right? And this is the estimator of this exact expectation that I call them here I. So if you, obviously you can show immediately that this is an unbiased estimator, and if you compute the variance of the estimator, you get something that looks like this. So we're going to have to make some assumptions to be able to compute this in some sort of analytical form so we can get some sense of what the correlation of the samples does to this estimation of the variance. So let me define a new variable zi that I'm going to call f of xi minus the expectation of f of xi. So obviously the expectation of zi is equal to 0. And I'm going to assume that these zi's are weakly stationary in the sense that their variance for all I is equal to sigma squared, and that the expectation of zi zj is sigma squared times rho evaluated at the distance between j and I. And I use an absolute value. So you can appreciate that this rho that I have here, this function, is the normalized autocovariance function. I have pulled sigma squared outside, so this is the normalized autocovariance function. So before I give you the calculation, let me just do a little plot. I'm going to take the covariance between f of xn and f of xn plus s. So s time steps after n. So I'm going to try to see how f of xn is correlated with f of xn plus s. And so that's the definition of the covariance. And if I divide this by the variance of f, which is really this autocovariance function for s equal to 0, okay? So if I normalize basically the autocovariance function, I get this rho, which is the normalized autocovariance function. Now, looking at this plot of this normalized autocovariance function, obviously because it's normalized, it starts with 1, and then it decays as s increases to 0. And you can appreciate that there is a certain m below which this autocovariance function is very small. So effectively there is a step, a time step m, so that the sample f of xn and the sample f of xn plus s, or simply the sample xn and x of n plus s, they're independent of each other. So you can see that you need to take m samples before you make xn and xn plus m to be independent of each other. So you do anticipate some deterioration in the variance of the estimator that you get using a Markov chain, simply because your samples are not IID. So let's see this calculation. I can take this and write this, this variance in terms of zi, so there will not be any expectations left. So the variance of my estimator is 1 over squared, this double summation of the expectation of zn zm. And then what I can do is I can write the summation for the terms first when n and m are the same, all right? And you remember when n and m are the same, I am going to get this normalized autocovariance function rho at 0, which is 1 by definition. And then you're going to get 2 times this summation, and I have 2 times here to account basically for n being greater than m, and also for the case when m is greater than n. And if you do the summation carefully, and you can follow the slides, and there is nothing complicated. It turns out that the variance of the estimator is sigma square over n times this big term inside this parenthesis that is called the autocovariance time. So the variance of this estimator for a Markov chain is not sigma square over n, but is sigma square over n times t subscript f, right? That is the time that it takes basically for two samples to become independent. Now, as we discussed in the schematic, if S is very large, right, in the particular case, if S is much greater than M, this autocovariance becomes equal to 0. And in some sense, again, you can consider then that samples x0 and xn, where n is much greater than m, they're basically totally uncorrelated. Okay, totally uncorrelated. I called them before independent, but really, since we do these calculations in terms of expectations, we're referring more precisely here to uncorrelated random variables. Okay, so let's, again, remember that we want to construct a Markov chain that, asymptotically gives us samples from a target distribution that I call here pi of x, and we want basically to be able to compute estimators like this that asymptotically give us the exact expectation, and this requires to come up with the proper transition kernel that has the distribution pi of x as its invariant distribution. So we need to find a k for a given pi that asymptotically the samples that we will get in the Markov chain are samples coming from the distribution pi of x. So the Metropolis algorithm actually does this for you rather automatically, and the original algorithm is given by this paper that we see here from a very old paper from what year is it? 1953, and this paper has been cited as of a few days ago when I reworked the slides more than 42,000 times. So that tells you that Metropolis algorithm was relevant in 1953 and is extremely relevant today for Monte Carlo estimation as well. Okay, so why is the algorithm extremely powerful? Because effectively it is very general. It allows us to actually sample from any pi of theta. So the algorithm will actually design the kernel that has pi of theta as a target distribution automatically. So it's an algorithm that requires a proposal distribution, but this proposal distribution, as we will see that I call here Q, doesn't have a lot of constraints. So in many ways, the algorithm is much more general than Gibbs sampling. And of course, both for this proposal distribution and the transition kernel, we need to satisfy constraints that look like this, which are common sense. So Q theta comma theta prime is the way we sample proposals theta prime given theta, all right? And obviously, because from theta we have to go to some theta prime, when you integrate this over theta prime, you should get 1. And the same, of course, is going to be true with the transition kernels. I am going to talk about the difference of the transition kernel and a proposal distribution in a little while. But this is the constraint that we need to satisfy. And then the algorithm, in addition to Q, has also an acceptance probability. So you use the proposal distribution to draw theta prime given theta, and then there is an acceptance probability. So you either accept the sample theta prime, or you reject it and you stay at the sample theta that you had at the previous time or at the previous stage in your iterative process. Okay, so let me just write down the whole of this Metropolis, the generic Metropolis algorithm. It's extremely simple, and here's the idea. We have a proposal distribution, and again, the notation is given theta, I use this proposal distribution to sample theta prime. And this proposal distribution can be symmetric or not, which means q of theta comma theta prime doesn't have to be in general equal to q of theta prime comma theta. So you sample in any way you like theta 0, and this can be maybe you set it the way we did in the previous example, theta 0 equal to 1000, or maybe you sample it from some Gaussian, so it can be a deterministic sampling, or it can be it can be a deterministic setting, or it can be a sample from some distribution. And the algorithm at iteration I proceeds as follows. So we assume we have theta iteration I minus 1. So we use the proposal distribution to sample theta star. We evaluate this acceptance ratio that I know it may look very weird, and until you see the proof that this actually works, it may be a mystery, but this is the acceptance probability. So it's the mean of 1 and this term that you see here. And then you either accept with this acceptance probability and you set theta I, so at iteration I theta star, or you basically remain, you set theta I at theta I minus 1, so you remain at your previous sample at iteration I minus 1. A few observations before you see any details, and again we're going to have to wait to see why this works. And obviously works means that this algorithm designs, it gives you a transition kernel K that somehow asymptotically will result in samples that come from the target distribution pi of theta. Okay, so we are going to have to wait for a while to see that, but you notice we need to evaluate for this acceptance ratio, we need to evaluate pi, and interestingly enough, the way that this acceptance probability is written, you can extrapolate here that somehow you don't really need to know pi, with its normalizing factor. And the same is true actually for Q. So easily we can use, instead of pi, we can use pi star, because this you can see that there is a ratio of pi's and a ratio of q's, and this will allow us to work with distributions that they are known up to their normalization factor, and that is very convenient, and it follows also algorithms, Monte Carlo algorithms that we discussed earlier on. Okay, now I mentioned we don't really need to know pi up to, we don't need to know the normalization factor, and this is very handy when you work with complex distributions coming from Bayesian inference. So if your target distribution is a posterior, you don't need to worry to have to actually compute the normalization of your posterior distribution. So just using the likelihood times the prior will be sufficient to be able to implement the Metropolis-Hastings algorithm. Now, this proposal distribution, at least up to now, can be anything, so there is significant flexibility, much beyond what we have seen for Gibbs sampling, where I remind you that the proposal distribution were basically the conditional distributions of our target distribution. So here, literally, this proposal distribution can be anything. And when I mean anything, I'll give you an example. You can sample theta prime, let's say, from this Gaussian distribution that has as mean some function of your previous theta. So this function of your previous theta can be some complex model. For example, can be a neural network, or maybe phi of theta can be the local maximum of your target distribution that is closest to your previous sample theta. Can be literally anything you want with some limited constraints, as we will see later on. So the flexibility is way above the one that we have seen for Gibbs sampling. And also, let me just say that the Metropolis-Hastings algorithm is a stochastic algorithm, because even if you draw, if I can go back to the previous equation, if let's say at two different iterations of the algorithm, you draw the same theta star from the proposed distribution, all right? Still the outcome of this algorithm at those two different iterations will be different, because even though you drew the same theta star, there is a probability of acceptance or not, all right? And that makes a difference, makes the algorithm to be basically a stochastic algorithm, all right? So the algorithm by its nature is a stochastic algorithm. So let me start with the original version of, and the simplification of the Metropolis-Hastings algorithm. And the original version of the algorithm is what's called the Metropolis algorithm, and that's what was actually included in this original paper in 1953. So let's assume that the way we design this proposal distribution is following what's called a random walk. So theta prime is theta plus some Gaussian noise, or actually can be a noise coming from any distribution f. So the proposed distribution in our case, so the proposed distribution of sampling theta prime from theta is actually my distribution f computed at theta prime minus theta. So the acceptance probability, if you substitute q of theta prime minus q of theta prime comma theta to be f of theta minus theta prime, and q of theta comma theta prime to be f of theta prime minus theta, you get an acceptance probability that looks like this. So look now what simplification is included in the original Metropolis algorithm. So the original Metropolis algorithm assumes that this distribution f evaluated at theta prime minus theta and at theta minus theta prime gives you the same result. So basically we're assuming that the proposed distribution here is a symmetric proposed distribution. And you can appreciate actually if this distribution f is a Gaussian, because in the Gaussian you're going to have theta minus theta prime squared, so it doesn't really matter if it is theta minus theta prime squared or theta prime minus theta squared. This equation will be true, and if this is true, then the acceptance probability is simply the minimum of 1 and the ratio of pi of theta prime divided by pi of theta. So this is the original Metropolis algorithm that is based on random walks and symmetric proposal distributions. So if you want to see the algorithm actually written for this simplistic case, I'm repeating the same algorithm, cut and paste from before. The only thing that is different, as you can see here, is that the acceptance probability does not contain any q, because effectively the q terms have been cancelled out, and the q only comes in selecting your proposed theta star starting from a state theta I minus 1. Everything else literally remains the same as what we had for the general Metropolis-Hastings algorithm. Now, there is another simplification of the Metropolis-Hastings algorithm, and this simplification goes with the name independent proposal. So let's see what an independent proposal is. You remember we select, given theta, we sample theta prime. So if the distribution, if this proposal distribution from we sample theta prime doesn't depend on theta, then we call this an independent proposal. And in this case, you can actually see this will become equal to q theta, all right? And so this is on the denominator, so this will go up to the numerator, and this will become q theta prime, which you see here. So my acceptance probability becomes the minimum of 1, this pi over q evaluated at theta prime divided by pi over q evaluated at theta. And you can appreciate once more that actually you can use this normalized pi star and q star the same way, for example, we did with rejection sampling. And also you can start appreciating that in similar ideas to what we had for rejection sampling, this ratio of pi over q has to be upper bounded for this method to work. So pi star at theta divided by q star of theta has to be less or equal to some constant m. So if this thing is not bounded, basically this algorithm is not going to work at all. Now, there are many other situations that you will see that this independent proposal is not going to work, because effectively you are not accounting where you are when you sample theta prime, and that obviously can be a problem. But then on the other hand, we will see benefits on maybe mixing this sort of independent proposal with the standard Metropolis proposal that we discussed a few slides earlier. And I'm going to come back to this later in this lecture. So let me just provide a comment here, right? So in the independent proposal distribution, the sample theta prime is sampled independently of where the previous sample was, okay? So in some sense, somebody can extrapolate and say, then maybe theta prime is independent of theta, right? If my proposal distribution doesn't depend on theta, so basically my two samples are independent, which means the autocorrelation is 0, the convergence is optimal, and all of the above. Is that a correct statement? The answer is, it is not a correct statement, because even though if I can go back actually to this algorithm, even though I am sampling theta prime independently of theta, you notice the acceptance probability depends on both theta prime and theta. So effectively, you're not going to be getting basically autocorrelation to 0, and you're not going to be getting a convergence that is optimal. In addition, using this independent Metropolis algorithm, if the proposal focuses in a region of low probability mass, it will spend most of its time there. Now, let me consider sampling from the posterior and see if we can use this independent proposal. So the posterior is written here. Again, we don't need to know the normalization factor. So what I'm going to do is I'm going to accept, I'm going to take as an independent proposal distribution to be the prior of theta, okay? So I am going to use basically the Metropolis algorithm, okay? And I'm going to use as an independent proposal the prior of theta, and this is what I have here. And you can see immediately when you put all the terms correctly. So this is the target distribution, evaluate at theta prime, the target distribution at theta, and then the ratio of your q's becomes pi of theta and pi of theta prime. So the priors are cancelled out, and then you get an acceptance ratio that is the minimum of 1 and the ratio of the likelihood evaluated at theta prime and theta. So will this work? Of course, this has all the limitations of the independent Metropolis algorithm that we discussed before, and obviously, this will make sense when the posterior is close to the prior, because we use a proposal distribution that is equal to the prior, and somehow, if I can go back, again to the general independent proposal, if you look at this acceptance probability here, you can appreciate the same way that we work with reject methods, that this method makes a lot of sense when Q is very close to pi. So in our case, in Bayesian inference, if we're going to use the prior as this independent proposal, this will actually work when that prior is very close to the posterior, which effectively means that the effect of the likelihood is insignificant, which actually would not be the case if you have a lot of data. So the idea there is that algorithm maybe useful only if you have limited data. All right, so let's go back and see why is and how is this Metropolis algorithm works, and why does it give us samples that come from the target distribution pi of theta. You remember to show that we do get samples that are coming from the target distribution. We need to show that pi of theta is the invariant distribution of this transition kernel K. So we need to show that this integral of pi of theta K of theta theta prime d theta is pi of theta prime. And the question is, and what is this transition kernel, right? Because up to now, somehow I have left it on the air, and I mentioned obviously the proposed distribution of sampling theta prime given theta from Q of theta comma theta prime. But what is the transition kernel? Is the transition kernel the same as the proposed distribution? The answer is no. So the transition kernel, it is not the same as the proposed distribution, because the transition kernel needs to account the cases where the proposal that is sampled from the proposed distribution is accepted, but also needs to account for the case when this proposal theta prime is not accepted, and you stay at the previous sample theta at iteration I minus 1. So now, not only we're going to have to show that pi is the stationary distribution of this transition kernel, whatever that transition kernel is going to turn to be, and I will give you an analytical expression in a second, but also, as we remember, we need to show that the Markov chain produced is irreducible, and I remind you, irreducible means that you can reach after a finite number of steps any region that has non-zero probability, starting from anywhere. And then obviously we need to show that the Markov chain is aperiodic. So we need to be sure that we don't visit the space in any periodic fashion. So let's concentrate first on this, and then we will come back and discuss a little bit about this irreducibility and aperiodicity. And we will see the last two conditions are actually very mild and very easy to satisfy in the context of the Metropolis-Hastings algorithm. So here is the transition kernel. Okay, it looks complicated, but actually, if you look carefully, it is not that complicated. So, transitioning from theta to theta prime, right? We have two different possibilities that may happen. One is, of course, given theta, we sample theta prime, and then we accept. Okay, that's one possibility. So that's the probability of transitioning from theta to theta prime when we accept. But then there is another possibility that we're transitioning from theta to some other location u anywhere in the sample space, and we reject. All right, and in that case that we reject, we stay at the previous sample theta. So this big parenthesis is the rejection probability. And if you don't see this, because this integral of q of theta comma u du is equal to 1, all right, by effectively the definition of the proposed distribution, you can put this inside, 1 inside the integral, and you can write this 1 minus alpha theta comma u times q of theta comma u du. So you move from theta to u, then you reject u for all possible u's, okay, so that's the rejection probability. And then this says, once you reject those u's, then you have to stay at the previous sample location theta. So that's where this delta function comes. Now, this transition kernel that you see here, it's a little bit mathematically incorrect, right? Because as you know, when you look at the probability of being in any given location, that is 0. So effectively, when you say you transition from theta to theta prime, it will make much more sense to have some integrable component here, and I'm using here d theta prime. So the idea here is I am moving from theta to the neighborhood of theta prime. So this is a little bit mathematically more precise notation, but again, this is a more elegant way, and this is what we're going to use in the analysis in the lecture today. But keep in mind, again, when we write this, literally what we mean is what you see on this second equation. All right, now remember the transition kernel, like the proposal distribution, also has to satisfy this equation, right? If you transition from theta to theta prime for all possible theta primes, this has to be equal to 1. I mean, if I am at state theta, I need to transition somewhere. So that integral has to come to be equal to 1. And actually, you can show that this is coming directly from this transition kernel. So if you take the integral of k of theta theta prime d theta prime, so you're going to have the integral of this d theta prime, and then this times this integral of this delta function. This comes to be equal to 1, and this integral, that integral cancel out, and you get, of course, 1, and so that equation is being satisfied. Now we need to prove that pi is the invariant distribution of this transition kernel that you saw before. And I remind you that an easy way to show that this kernel has pi as its invariant distribution will be if somehow we can show that this kernel is reversible. And reversible being, it means pi of theta k of theta theta prime has to be equal to pi of theta prime k of theta prime comma theta. In words, that means if you are at theta and you move to theta prime, that probability has to be equal being at theta prime and transitioning to theta. Or if you write like this more generally, if you are in the domain A of your sample space and you move to B, to domain B, that probability should be equal being starting at B and moving to domain A. So we're going to have to prove that pi of theta, k of theta theta prime is equal to pi of theta prime, k of theta prime comma theta, and that condition is called the detail balance equation, and we have seen this when we discussed Gibbs sampling. If the detail balance equation is satisfied, then immediately you can show that the transition kernel has pi as its invariant distribution. And I'm going to show you that equation again as a review in a slide or two. So again, we need to prove that this is equal to pi of theta prime, k of theta prime theta. And the way to do it is to take each of these terms separately and show this calculation for each of the terms. So if I take, so here what I have done, I took my transition kernel, I multiply everything with pi of theta. So if I take this first term, all right, so I'm going to have to prove that this is equal to pi of theta prime, a of theta prime comma theta times q of theta prime comma theta. So if you use your definition of the acceptance probability, you put pi of theta and q of theta theta prime inside this minimization, and then you pull outside the minimization pi of theta prime and q of theta prime comma theta. Then effectively you can show immediately that the detail balance equation is satisfied, at least when you look at this first step. Now you can immediately show actually because of this delta function that allows you to interchange theta with theta prime, you can show the same is true when you use this second term. So effectively we can show that the detail balance equation for this transition kernel it is satisfied. So basically pi of theta times k of theta theta prime is pi of theta prime k of theta prime comma theta. All right, so pi is the invariant distribution of the kernel, and this is what I mentioned before. If this detail balance equation is satisfied, you can immediately show that pi is the stationary distribution of k, because if you take pi of theta, k of theta, theta prime, and you plug it in here to be pi of theta prime, k of theta prime, comma theta, this is independent of theta, so I can move it out of the integral. And then by the properties of the transition kernel, this integral in theta basically gives me 1, so I get pi of theta prime. So if the reversibility condition is satisfied, then pi is the invariant distribution of the transition kernel that you see on the top, which is effectively my Metropolis-Hastings algorithm. So notice here that you may have many more kernels that they are p-invariant than they are p-reversible. But here, because to check reversibility it's easier, we start checking if we have pi reversibility, and if this pi reversibility is satisfied, then we can guarantee that the kernel has pi as its invariant distribution. But certainly there may be situations where this condition is not being satisfied, all right, and still pi is the invariant distribution of the transition kernel. All right, how about aperiodicity? So you remember aperiodicity means we do not visit the state space in any periodic fashion. And what I mean with that is, if I can concentrate directly on the equation that you see on the slide, let's say that you are in state theta at some time. You don't want, after a finite number of steps k, through your transition kernel defined by the Metropolis-Hastings algorithm, you don't want to return to the same location theta. And so when I mean here k to a little power k, I mean applying the transition kernel little k times, right? We don't want after little k times to come back to the original sample theta that we started with. So if that happens, all right, you can take the greatest common divisor of all the integers in this set, and that will define the period of state theta. And in our case, we will assume that our chains are periodic when effectively if you like, this period turns out to be equal to 1. Okay? Now, if you are curious as to what the Metropolis algorithm has to say regarding aperiodicity, let me just say this turns out not to be a problem, because at every sample from the proposal distribution, there is a finite probability that actually you will accept it or not. And that breaks this any potential for periodic returns to the same states, because there's always, again, a finite probability that you will not accept the states that you sample from the proposal distribution. How about irreducibility? So irreducibility means that if you start at a given location, you want to be sure that after some finite number of steps, and I indicate them here as n, that somehow you can hit any region A that has finite probability. You need to be able to go from any location to any other location at a finite number of steps. You need to be sure that there is a non-zero probability with your transition kernel that you can hit this region A starting at any given location in your sample space. So there is a very simple way to actually satisfy this irreducibility condition in the context of the Metropolis-Hastings algorithm, and that condition is what you see here. So if you have a location where the probability of theta prime is non-zero, then you need to be able to enforce that the transition probability from theta to theta prime is greater than 0 for every theta. So basically you need to be able to have a proposal distribution that from any location it has a non-zero probability to go into any other location theta prime. Once that is satisfied, then irreducibility is taking care, and if irreducibility is taking care, aperiodicity is taking care, and you have a kernel that is reversible, then you have this ergodicity theorem that guarantees that asymptotically the samples that you get are samples coming from the target distribution, and the expectations that you compute with the samples basically converge to the true expectations under the target distribution pi of theta. All right, so that's again the irreducibility condition. We talked about the aperiodicity taken care of by this finite probability of rejecting any proposed sample from the proposal distribution. So you can see that the assumptions of the Metropolis-Hastings algorithms are actually not very strong, and in some sense you have a lot of flexibility as to what this transition kernel Q theta comma theta prime can be. All right, so the flexibility versus, let's say, Gibbs sampling is significant. All right, so let's start discussing some simple examples. So what you have here is a very simple situation. So let me remind you one particular algorithm that we will use here is, let's take a proposal distribution to be a Gaussian with a mean that is your previous sample. So this is like a random walk, all right? This is a random walk, and the noise variable is a Gaussian, okay? So I am going from the location x to x nu with some noise variable, right, that comes from a standard distribution, but here I have the noise variable being s squared, okay? So s squared effectively will define how big are the steps from x to x nu that I'm going to be making using this proposal distribution. So I'm going to start with the original Metropolis algorithm that you can appreciate here that this proposal distribution is symmetric. So in the acceptance probability, the q terms disappear. So basically the acceptance probability becomes the mean of 1 comma pi of x nu divided by pi of x. So you accept or reject with this probability, which, as you remember, the way you implement it, you sample a uniform random variable from 0 to 1, and if u is less than this acceptance probability, you accept, right? That means your new sample becomes, x nu, otherwise, basically, you stay at the previous location x. So let me show you the results of this. For a mixture of two Gaussians that you see them plotted here, and I play with the values of s, starting from on this right lower corner with very small s, and on the upper left corner a higher s. So you can appreciate that when s is very small, effectively you don't do anything but exploring one of the Gaussians, and you never really jump to the other Gaussian. So as s increases, then you once in a while you take jumps to the other Gaussian, you stay there, you explore it, and then you move back and forth between the two Gaussians. So obviously the choice of s here is fundamental to make this type of algorithms to work, especially when you have this mixture of distributions that you see here. Okay. So usually when you have random walk, these increments that you do are very small. So the samples that you generate from the Markov chain are correlated, and the acceptance rate is expected to be rather high. That's usually high, means usually between 0.5 to 0.7. And again, as I show you in this mixture of two Gaussians example, you need to select the steps in the random walk efficiently, so you can explore all the regions where you have non-zero probability mass. Certainly in the two Gaussians before, you need to be able to jump from one Gaussian to another. So let's visit another Gaussian mixture here. That comes with two Gaussians with ratios of 0.25 and 0.75. So this is the mixture of these two Gaussians. So I'm using a proposal distribution, and I'm taking again as the sigma in my proposal distribution to be equal to 5. I am starting with the location, a deterministic location equal to 0. And then you see the distribution of my samples. So it seems for this particular case, I am getting a histogram that is very close to my target Gaussian mixture. You see the expectation of x, which is 0.75. is computed, rather well in this plot on the upper right part. And then you see also this autocovariance function normalized, and you can see that the after very few steps, like 10 steps, the samples that you get are independent in comparison to the original sample at the location here. If you change sigma to a huge number, 50, now suddenly you see that the autocorrelation is very high. The acceptance ratio is very small, all right? So the idea here is you do very big steps and that are mostly rejected, and of course the convergence rate is very slow, okay? And if you use, on the other hand, a very small sigma, again you notice the acceptance ratio is very high because you do very small steps, but if you do very small steps, you only explore one of the modes of the distribution. You can see that the the autocorrelation is very high and the convergence is very slow because the samples are very highly correlated. So let me take another target distribution here. So the target distribution is a Gaussian. Again, I'm using a normalized Gaussian, and I'm taking as a Metropolis-Hastings proposal to be this Gaussian with a noise variable here 0.2 and another Metropolis-Hastings algorithm where the noise variable is equal to 5, and we want to see how easily or how efficiently we can get samples from this target distribution by using these two proposal distributions, Q1 and Q2. So using Q1, you can see this is what you get for the expectation and the variance. This is the histogram that you generate, so it looks very close to the target distribution. And in this particular case, if you use Q2, you can compare again. This expectation here is 0.034. This expectation is 0.01. So for the same number of samples, obviously, you can see there is a significant difference in the estimates that you drew of the true expectation, and also the variance here when you use the distribution Q2 is 1.00. The variance here is 0.93. Okay, another example with a Gaussian mixture, and you can see that here the Metropolis random walk proposal distribution is capable of jumping from one of the modes of the Gaussian mixture to the other. So this gives you very good approximation of this mixture of the two Gaussians. But here is a situation where effectively you start at one mode of the distribution, you do very small random walk steps, and you never explore the second mode. So we will see before the end of the lecture today that somehow you will benefit if once a while you can have another proposal distribution, an alternative to this random walk that somehow takes you to this mode. So then with random walk you can explore it, and then using the other proposal distribution you can jump back to the other mode. So this will lead to ideas of using hybrid or mixture of proposal kernels, as we will see a few slides from now. So in this random walk, the acceptable basically rate of acceptance of samples is between 0.2 and 0.4, and of course you may think, because that noise variable sigma squared controls if you do small steps or big steps, you may think that somehow you can actually go and control these steps during these iterations in the Markov chain, so you can actually achieve this acceptance rate, the optimal acceptance rate at every iteration. But if you do that, of course, you are going to break the whole idea of the Metropolis-Hastings algorithm. So the chain is not anymore going to be Markov, and all the convergence properties will be lost, and basically what you will get by playing with sigma squared during the iterations will be effectively garbage. Now, one of the things that you can appreciate, especially when we talked about this independent Metropolis-Hastings algorithm, you will benefit a lot if this proposal distribution, the random walk that you do with the proposal distribution has heavy tails, all right? So that way you can prevent being trapped in local modes of your target distribution. Now, I haven't said really anything about high dimensional applications. So if your distribution pi of theta is high dimensional, there is no guarantee that as we have this primitive algorithm will work. And of course, the task on selecting an appropriate transition kernel q of theta comma theta prime for a high dimensional distribution is anything but trivial. So we may need to do something on this, and that something may be similar to what we did with Gibbs sampling, where effectively maybe we update each of the components of the target distribution, maybe one at a time, using ideas similar to what we did with Gibbs sampling. So let me give you a few examples with the independent Metropolis algorithm. Again, my target distribution is the same as before. I am taking Q1 to be like this. I remember in the independent Metropolis-Hastings algorithm, the selection of theta prime, doesn't depend on where you are at the previous time step or the previous iteration. And notice that pi over Q1 in this case is unbounded, so we expect this to give us trouble. And if you take Q2, then easily you can see that pi over Q2 is bounded. So let's see what type of results we get. So when you have Q1, you basically, if you create a histogram from your Markov chain, it doesn't look anything but the target Gaussian. If you use Q2, then things look way better, and you do get samples that correspond to your target distribution. All right, and again, maybe that's my last example on the Metropolis-Hastings algorithm. I am again using the same Gaussian mixture that I had before, and I am going to use an independent proposal again. So again, the selection of the next sample doesn't depend on the previous sample. So my independent proposal is a Gaussian center at 0 with some noise variable sigma squared. Now, you remember, because this independent proposal does not depend on where I am, all right? Depending on the values of sigma square, this independent proposal has the potential in the Gaussian mixture to jump from one mode to another. Okay, and that's exactly what happens with this Gaussian mixture. So you can see the autocorrelation, this autocovariance function computed for the case of sigma equal to 1, and this is for the case of sigma equal to 10. And again, if you take an estimation, an approximation of the expectation, you can see the case of sigma equal to 10 converges to the correct value. The case of sigma equal to 1 does not. Okay, so if you use sigma to be a high value, you can jump from one mode to another, and that allows you to get very good representation of the target distribution that in this case is a Gaussian mixture. So it turns out that the acceptance ratio for both proposal distributions here is about 0.24, but only the case of sigma equal to 10 seems to be working well. All right, let's start talking on how we can extend these ideas of Metropolis-Hastings algorithms and talk about this idea of using a mixture of proposal distributions. So we showed before these random walk steps, right, that we go from theta to theta prime on small steps, but then we show this idea of this independent proposal distribution that allows us to make big steps. how about then if we use a proposal distribution that is a mixture of a proposal distribution that is an independent proposal distribution, it depends only on theta prime, and then we have a standard Metropolis-Hastings proposal distribution Q2 theta comma theta prime. Lambda here is a scalar between 0 and 1. Okay, so you can actually show that this algorithm satisfies all of the properties of the Metropolis-Hastings algorithm, right? This will correspond to one of the kernels, this will correspond to another kernel, and so you will get basically everything we have discussed, and this is a valid proposal distribution. Now, how about if instead of a proposal distribution that is a mixture of two proposal distributions, you go directly and use a mixture of transition kernels? So effectively, this is like using a mixture of two Metropolis-Hastings algorithms, one that has a transition kernel K1 and another one that has a transition kernel K2. Now, it turns out that this is much more efficient than the case where you had a mixture of proposal distributions, and the algorithm is computationally cheaper, and of course you can show that the invariant distribution of this mixture of kernels is the target distribution pi of theta. So indeed, if you if these are both valid kernels, Metropolis-Hastings kernel, and you substitute this k with this mixture of the two valid kernels, you can see the first integral will give you pi of theta prime, the second integral will give you pi of theta prime, and when you take the averaging, you get pi of theta prime. So pi of theta is the invariant distribution of your mixture transition kernel. Okay. So so this is very powerful, right? We can take two kernels, mix them together, and then we combine them, and we produce a new transition kernel. You can actually push this to extremes, and what do I mean to extremes? You can take the case, for example, one of the kernels, right? You don't update things. You stay where you are, all right? And the other kernel is your regular Metropolis-Hastings kernel, okay? So this K1 is irreducible and aperiodic and follows all the properties that we discussed before. But let's say K2, K2 is, it says you transition from theta to theta prime, but that transition leaves you exactly at the previous location theta. So it turns out that if either K1 or K2 are irreversible and aperiodic, you can show that this mixture of the two kernels K is irreducible and aperiodic, but actually the opposite is not true. So if K is irreducible and aperiodic, it does not mean that K1 or K2 are irreducible or aperiodic. So effectively, the requirement here that one of the two kernels is irreducible and aperiodic, it is a sufficient but not necessary condition for the mixture of the two kernels to be irreducible and aperiodic. So this is the mixture of two kernels, but actually you can also do composition of the two kernels. And what I mean composition, here is an integral equation defining the composition between kernel K1 and K2. And the way this composition works, or the way that you're going to sample theta prime given theta, the way that this will give you the probability of theta prime given theta is you're going to be sampling this variable z, so think of this as a latent variable given theta, and then for a given c, from the kernel K2 you're going to sample theta prime. This is what I have in the first equation, and this is how this composition of these two kernels is going to work. Now, in this particular case, both kernels K1 and K2 have to be p-invariant for the composition to be p-invariant, and you can see actually the proof of this in the equation on the bottom. So if you try to check the p-invariance of the transition kernel k, that is this composition of the two kernels, you can plug in this integral in here, and with some rearrangement, using the fact that k1 has pi as its invariant distribution, that first integral will give you pi of z, all right? You transition from theta to z, and this second integral then is going to give you pi of theta prime. So if both kernels k1 and k2 are p-invariant, then the composition is going to be p-invariant as well. So we have now this flexibility of using mixtures and compositions of kernels, and of course this is going to be extremely important to address the extension of the Metropolis-Hastings algorithms to high-dimensional distributions, and also address some of the challenges that we discussed before on choosing the proper proposal distribution Q to allow us to sample theta prime given theta. Right? We have seen, for example, in the Gaussian mixture case, we would like once in a while to be able to jump from one mode to another, but maybe when we are in one mode, we would be happy to actually use a random walk with small steps so we can actually explore that local mode better. So let me give you an example with the target distribution, a very simple target distribution of two variables, theta 1 and theta 2. So we can use a composition of two kernels. K1 will update theta 1 only, and will keep theta 2 to be fixed. And then kernel K2 will update theta 2 and keep theta 1 fixed. Obviously, we can do this either by using a mixture of the two kernels, or we can use composition of the two kernels, and you can produce different algorithms that way. And also looking at those two steps here, that immediately reminds you the way Gibbs sampling works, right? Where you remember we update one component at a time, but I remind you the way Gibbs sampling works is you sample in every step using your conditional distributions. Here there is no limitation actually on what these kernels K1 and K2 that allow you to sample from each component are about. So the flexibility is of course significantly higher than the flexibility that we had on the Gibbs sampling algorithm. So let me continue this example of two random variables. So we have a pi of theta 1 and theta 2, and I'm going to give you two transition kernels that update one of the variables at a time. So let me take a proposed distribution, all right, that is associated with the kernel K1 that updates only the component theta 1, leaving theta 2 unchanged. So this proposed distribution, I am writing here Q1 bar, takes me from theta 1, theta 2 to theta 1 prime, theta 2 prime, but theta 2 doesn't change, that's why I have this delta function, and the transition is only from theta 1 to theta 1 prime. Now what you can do is you can go and compute the acceptance ratio for this proposed distribution, and that acceptance ratio will be the minimum of 1 and R1 of theta prime, where R1 is given by this ratio. And the only thing I am doing in the calculation that you see here is plug in this proposed distribution for this kernel K1 that updates only theta 1. And you can see here I have a delta function, theta 2 and theta 2 prime, so I can go where I have theta 2 prime and plug in theta 2 instead, all right? And that's what I have here. And then immediately you can see, because theta 2 is common on both of this, I can write, let's say, this as the conditional of theta 1 prime given theta 2 times pi of theta 2. And I can write this as the conditional of theta 1 given theta 2 pi of theta 2. So pi of theta 2 cancel out, and this is what I get. So now you can appreciate that this kernel K1, or this proposed distribution that you see on the top, effectively they give you, at every step, basically they give you a Metropolis-Hastings step, but now the invariant distribution is the conditional of θ1 given θ2. Okay, so after all of these cancellations, you can see that now your invariant distribution is pi of θ1 given θ2. θ2 doesn't change here, so the invariant is pi of θ1 given θ2. Now, keep in mind that when you're going to implement this algorithm and you're going to do the updates of θ1 and θ2 iteratively, in every step, let's say at the step where you sample from this Q1 bar, right, you're only going to do one step of the algorithm. So you're not going to pull this iteratively to convergence to this conditional distribution. Okay, so even though it looks that the target distribution is the conditional, we're only going to do one step at a time when we use a composition or a mixture of these kernels, K1 and K2, and you will see this again when I provide a summary of the overall algorithm. Let me do the same thing with K2 that updates only θ2. θ1 in this case remains the same, θ2 is updated to θ2 prime, and when you do the same things about the acceptance ratio, it turns out that in the acceptance probability, you actually get what looks like a Metropolis-Hastings step, but now the invariant distribution is the conditional of θ2 given θ1. So here is how the algorithm looks like, where you're going to be doing one update of θ1 using Q1, and then immediately an update of θ2 using the Q2. Okay, and remember, when we update θ2, θ1 has already been updated on step 1. So step 1 again is start with your samples at the previous iteration, compute the acceptance probability. All right, this is what I have here, compute the acceptance probability. By the way, I haven't really done anything here but change only the notation from what I gave you earlier for, that's my that ratio R1 that I had 2 slides ago. So with probability alpha 1 I accept, and I set θ1 at iteration I to be θ1 star. Otherwise we keep θ1 to the previous iteration, and θ2 in this step doesn't change. At the second step, we're going to sample θ2 star from Q2, and I want you to pay attention that θ1 has been updated from the step 1 of the algorithm. So everywhere you see θ1, this has been updated from the previous step, but θ2 is at the previous iteration, and now we want to update it to θ2 star. So with this probability you accept θ2 star, otherwise you stay at the previous step. So that's this composition of the two Metropolis-Hastings kernels, and I haven't really said much as to what those two kernels are, but we emphasize that basically the target distribution is or the invariant distribution. In one of them is the conditional pi of θ1 given θ2, and in this case what you see on this slide, the invariant distribution is pi of θ2 given θ1. Now you can mix those things together, all right, and the same way we work with Gibbs sampling. So what you can do is you can start updating components you remember we have a target distribution of θ1, θ2, so you can start updating components randomly. So you start sampling this index j from a uniform distribution over indices 1 and 2. So this is, so if j equal to 1, you will update θ1, if j equal to 2, you will update u2, and you will fix, so you will have to define, so at every time you will be updating θj star and all the other θs. So in our particular case, the other variable, because we have a distribution with two target variables, So the other variable is going to be kept to its previous value. But remember, if we are to update theta 2, that means maybe, you look, if theta 1 has been updated, you have to use whatever updated value you have. Okay, the other way around for theta 1 as well. So these are the other variables, all right? This is the acceptance probability for theta j star that you sample from the proposal distribution Qj. You accept and you update theta j of I with theta j star. Otherwise, you stay the previous values of theta j. So if you think again that if j is equal, let's say j is equal to 2, minus j here will correspond to 1. So this theta j star will update, of course, theta 2, all right? And theta 1 now will be exactly what I had before, right? It will be the previous values of theta 1, okay? And again, you notice here, I also have theta j I minus 1, so this will be the value of theta 2 at the previous iteration. What I suggest is use this acceptance probability and try to compare nodes with the acceptance probability when I sample with transition kernel K1 and K2 from the two previous slides. So set j equal 1 and j equal to 2, and you will see that the two formulas agree that, and this is sort of a more general way to write the algorithm where you don't sample in sequence, but you sample randomly. So you can update theta 1 and theta 2 in any order based on what samples of j you get from this algorithm. Now, you notice that in this algorithm, it's the same way when we work with Gibbs sampling, right? We update one component at a time. So these kernels K1 and K2 certainly are not irreducible or aperiodic. However, the composition, the way we have defined it, can be reducible and aperiodic because both of the components are updated. So the algorithm can be shown to actually work and converge to the target distribution. Now, if you have not a two-dimensional random vector, but you have theta to be with p components, you can actually apply the same algorithm that we discussed before, right? So you can update each of those components one at a time. So you can use a transition, a proposal distribution to update the k component that looks like that. So you keep all, these are all the previous theta parameters, all right? So you're going to keep all the previous theta minus k to their previous values, and you will only update theta k to theta k prime. And so if you do this, you will be able to extend this algorithm to high dimensions. All right, and of course, each step of this algorithm using this proposal distribution, the invariant distribution, will be the conditional of theta k given theta minus k. So given all the other thetas. But remember, the way these algorithms work, you do one Metropolis-Hastings step with this as the invariant distribution. You don't converge, so you don't keep iterating to converge to this conditional distribution. All right, so that's a significant element to remember. Now, let's say that we take these algorithms that we discussed before for a distribution with two random variables, and you update where you update each of the components separately. So let's look at the updating of theta 1 to theta 1 prime, keeping theta 2 to be the same. So let's define this, these proposal distributions to be equal, right, to the conditional distributions. So if you look at the ratio that you had in the acceptance probability, then this proposal distribution becomes the conditional of theta 1 given theta 2, all right? And this becomes the conditional of theta 1 prime given theta 2. So we designed this, right? We said, how about if this proposed distribution is the conditional, right? So I plug it in there, and you notice in that case, this cancels with this term, this cancels with that, and then this becomes equal to 1, which means the acceptance probability in this case is equal to 1, and actually the algorithm becomes nothing else but the Gibbs sampler that we have seen in an earlier lecture. All right, so let me summarize the general hybrid algorithm that allows you to use multiple kernels either in composition or as a mixture. So we have a general distribution with P components, and the way that this algorithm is stated here, it takes one component at a time, but as I indicated before, you can start updating these components in a random fashion. So here we're updating the component theta k. So we're going to use a Metropolis-Hastings step that has a target distribution, this conditional, all right? And the proposed distribution is going to look like this. All the other variables are going to be kept to their previous values, all right? We're going to update the value of theta k from the value at iteration I minus 1 to theta k prime. And again, this theta minus k, all the components up to k minus 1 have been updated. If we do this in sequence, they have been updated at iteration I. From k plus 1 to p, they have not been updated, okay? And again, this has as a proposal distribution the conditional of theta k given all the other thetas. All right, so and again, if we make these proposal distributions to be the conditionals, as I said before, we actually do get the Gibbs sampling. So what I want you to think about in this algorithm, right? You can think that some of the proposal distributions that you use can be your Metropolis-Hastings random walk, let's say, steps, and some other ones can be based maybe on, let's say, the conditional distributions, or they can be based on some other algorithm that allows you to explore the state space, the state space better. Okay, so this allows us to mix Metropolis-Hastings algorithms with many different algorithms. So you can think one step that looks like a Gibbs step and another step that looks like a Metropolis step. So this idea of using Metropolized Gibbs sampling, I had mentioned it in passing when we talked about the Gibbs sampling algorithms. It's a very important category. It's a very important category of algorithms. So again, if you have a distribution that has two random variables, pi of theta 1 and theta 2. So maybe one step you sample from the conditional the way you would do with Gibbs sampling, but then to sample theta 2, you sample with a Metropolis-Hastings step that has as a target distribution the conditional, but you don't sample from the conditional. Remember, it has as a target distribution, as a limiting distribution of the conditional, pi of theta 2 given theta 1, but on the first step you sample from the conditional pi of theta 1 given theta 2. So here is how this algorithm will look like. A Gibbs sampling on step 1, and then a Metropolis update for theta 2 on step 2 that has target the conditional pi of theta 2 given theta 1. And again, I emphasize this second step, you don't need to run it to convergence where your sample comes from this conditional. You just do one step alone. In this case, you do sample from the conditional. This conditional in the second step is your target distribution, but you simply get one sample through this Metropolis proposal that has a target, this conditional. So you never sample exactly from that conditional distribution. All right, we're almost done with the lecture, so let me mention a few other type of algorithms that Metropolis-Hastings has found significant extensions. So what you see here is, sort of a random walk, but is a random walk in regions that follow the gradient of the log probability of pi of theta. So this type of random walk allows you to sample of regions of high probability using gradient information, and this can be beneficial in many settings. Sigma squared here is selected to give you an acceptance ratio that's about 0.57, and the reason that this algorithm works is basically comes from the fact that if you take the continuous case of this equation that has this form, you can show that theta t has pi as the invariant distribution. All right, so you can do updates following the gradient of pi of the log of pi of theta, and asymptotically you'll be getting samples that come from the target distribution pi of theta. Now, what you see on the equation on the top is the acceptance probability for the general Metropolis-Hastings algorithm. You can literally extend this to other forms of acceptance probability, and people have done that in the literature. I can say that the Metropolis-Hastings acceptance probability is favored because it gives you an increased probability of accepting the sample theta prime, but certainly I want to emphasize that you're not limited in this form that you see here to make pi to be the invariant distribution of your transition kernel. So here's an idea. You can use any acceptance probability that has the following form. Delta of theta prime theta divided by pi of theta times your proposal distribution q of theta theta prime, where delta is a symmetric function, so delta of theta prime theta is equal to delta of theta theta prime, and of course you need to guarantee, because this is an acceptance probability, you need to be sure that this is between 0 and 1. So here is a possibility that it was discussed in a paper in 1965 by Baker, that the acceptance probability was taken to be what you see here. Obviously this is between 0 and 1, and you can see this delta theta theta prime becomes equal to this, and obviously if you change theta theta prime you can see this is symmetric, okay? And now you may wonder, since we prove that with this acceptance probability pi is the invariant distribution of the Metropolis transition kernel, how about using this generic form, right, much more general form of acceptance probability? Does it still make pi to be the invariant distribution of k? The answer is yes, right? So if you take your definition of k for general acceptance probability alpha that you see there, and you check the reversibility condition. I'm not going to go through the details. There is really nothing except using the symmetry on delta, and immediately you can see that pi of theta times k of theta theta prime is pi of theta prime k of theta prime theta. And I'm doing this for the first term in the kernel k, but the same type of calculation can also be shown for the second term with the delta function. All right, we're practically done, so I need only to tell you a few words about what's called the Metropolis proposal based on Hamiltonian dynamics. All right, so for those who don't know anything about statistical mechanics or atomistic modeling, maybe some of these ideas don't mean very much. So let me say that we're interested to sample x from some target distribution pi of x, and I'm thinking now to make the analog with statistical mechanics. I'm thinking of x being the location of atoms in space. So pi of x is really the Boltzmann distribution that has the form e to the minus some potential v of x of the location of the atoms. All right, so this is a Boltzmann distribution with an inverse temperature beta here equal to 1. Okay, and so we need to to sample from this target distribution that has this Boltzmann form. So, you know, particles have locations x, but also have momentum, and I'm going to call the momentum here P, and I'm going to assume that P follows a Gaussian distribution. So I take the mass here of these particles to be equal to 1. So the distribution of P is this Gaussian here with mean 0 and variance equal to 1. So if I take x and p to be independent random variables, their joint distribution follows the form e to the minus v of x minus p squared over 2. And for those who are familiar again with Hamiltonian dynamics, v of x plus p squared over 2 is the Hamiltonian. All right. So the idea then is, can we use the dynamics of the system? Can we use the way the atoms move in a space for described by a given Hamiltonian, and use the samples that we get from molecular simulations as the samples coming from the target distribution pi of x? And the answer is yes, we can. And let me just tell you how you're going to integrate the equations of motions to do that. So step 1, you sample the momentum from this Gaussian distribution, the way that I introduced before. So you sample the momentum independently of the locations of the atoms. Then you, for that Hamiltonian, you keep that energy of the system constant. You run a few steps of molecular simulations, and you see what the atoms do. You follow the trajectory of the atoms, and after some time, you record the location of the atom x. That location x gives you a sample from your target distribution pi of x. So effectively, we have an algorithm here that allows you to sample from a Gaussian the momentum, and then take as samples of x the result of a Hamiltonian dynamic simulation, a molecular dynamic simulation. All right. The only thing you need to be careful in implementing this, because we're supposed to, once you sample P, we work with constant energy system, so the Hamiltonian has to be constant, and so you need to have a solution of your Hamiltonian dynamics problem that keeps the energy constant, and that requires a particular integration of the Newton's equation to preserve energy, and the scheme that goes with the name leapfrog integration scheme is the scheme that preserves energy. So that's a little detail, but eventually this is a hybrid algorithm, right? You sample from a Gaussian, and then you integrate this with molecular simulations to sample to get a sample of the locations of the atoms. Okay, so the locations of the atom and the moments of the atoms are following this joint distribution that you see on the top of the slide. Now, this is a very, very active area of research, this Hamiltonian Monte Carlo type of algorithm. So for those who are interested for more readings, you can search on the web under Hamiltonian Monte Carlo, and you will come up with significant references on the topic. So that's where I will finish for today with the Metropolis-Hastings algorithm. It has been a long lecture, and we will move on the follow-up lecture on the state space model, and then from there we will discuss about a new category of Monte Carlo methods that go with the name sequential Monte Carlo methods. Until then, happy readings. Bye.